This video is going to look at total internal reflection, which is just kind of an interesting phenomenon that happens with light. So real quick, I want to review refraction. So refraction is when light bends moving between media. So if it moves from one medium into another, it's going to bend. So if it goes from faster to slower, it bends towards the normal line. And then if it's going from slower into faster, it bends away from the normal line. So we get this interesting effect. So if there's a significant difference in the index of refraction or in the speeds that they travel, either one is fine. So a significant difference in indices of refraction. Another way of thinking about it is a significant difference in the speed of light between the two objects. And the light is already at a shallow angle in the medium, or in the slower medium, if you want to add that. It can be bent so much that it actually reflects back. And this is called total internal reflection. And this will continue happening until it hits an edge with a steep enough angle. So what's happening here is, if I'm already at a low angle, or in other words, a big angle relative to the normal line, well, we already know that if it's going to go into a faster medium, what has to happen? It has to be bent away from the normal line. Well, if this is already really, far away from the normal line, and I'm going to get bent so that I actually hit along the normal line, if you plug in numbers, you'll be able to see this. I don't have any offhand, but if there's enough difference between the speeds of these, I'll get bent not just away from the normal line, but all the way to this, the surface between the two. And if that's the case, then instead what happens is I bounce backwards like this at the same angle that I came in on. And then, if it's a thin surface, then it might come down here and it's at too low of an angle, so it bounces back and bounces back and bounces back all the way down this object. And that's total internal reflection. So I want to talk about an example of this. First is fiber optic cables. So these are, if you've got a cable, it's made of a very, very thin, flexible glass. But what ends up happening is, because the speed of light is fairly slow in glass compared to air or compared to whatever else would be outside of this, then if I shine in light at this side, basically along a straight line, then what ends up happening is it goes in a straight line, straight line, straight line, straight line, hits the side, but it's so shallow and the difference is so great that instead of refracting outwards, it gets reflected back inwards, continues until, I hit again. And what's good about this is I can bend this, I can reshape it, it can be curved. As long as it doesn't have any really steep bends in it, we'll end up getting the light just kind of bouncing back and forth as it travels down this cable until it gets to the edge, and now suddenly we're traveling almost straight compared to the edge, and so what happens? It pops out the outside. So the place you've seen this, they're not really popular anymore, but back 20, 25 years ago, you'd see these little devices, and then they have all these little plastic tubes coming out the top, very thin. And then there'd be a light underneath, but then these would have total internal reflection, so you just see the ends of these pieces of plastic light up in all these different colors. But there wouldn't be light coming out the sides of the tubes, just the ends. You also sometimes see they have like handheld ones of these. You might see toys of like little wands with little plastic bits. If you wave them around and then the ends light up because there's a little flashlight inside the handle. The main place that this is practically useful though is fiber optic cable for internet or for any other type of signal. We can basically shine light in one end and then it travels through and then comes out the other. And unlike, say, electrical signals, this loses very little energy, very little clarity over the entire length of the cable. And because, even though it is glass, if you make the glass thin enough, it can actually be flexible and bend, and you can route it through different stuff. But that being said, glass is still glass and still fragile, so fiber optic cables are more fragile than traditional like wiring that you use to carry signals. But that's what the point here is that it bounces off the edges here and travels out. A second example would be a gemstone. So let me draw kind of draw a real basic kind of diamond or gem shape. And this is not going to be as easy to sketch out what's going on here, but we'll make it clear. So when they cut these, if they cut them well, basically what ends up happening is all of the faces are kind of aligned relative to one another, so that whenever light goes into the gem from a given face, it will tend to be set up so that then, faces opposite will cause it to reflect. And so what you end up having is a lot of total internal reflection. So light is just constantly bouncing around in here. And then if it's just lined up right, it comes out at very concentrated or very specific places. And that's what makes them sparkle, as it were, is because light is coming in from all angles, but it's only coming out in very specific places when certain faces are lined up. So maybe only when you're looking from this side and light is bouncing off of this point does it come out. And so that's collecting all the light that's kind of bouncing around randomly and then just popping out here. It's a little hard to explain the details because it ends up being just a lot of geometry. But I wanted to give it as an example. That's why it sparkles, because it's only coming out at certain places. So as you turn the gem or as you look at it from different angles, you're getting different places that total internal reflection is popping out of. And then kind of in between the sparkles, no light is coming out to hit your eye. So that's really roughly what's going on with any sort of gemstone here.